Hello everybody and welcome to Blockchain Expert. In this video, I'll be going over proof of work. Now to put it simply, a proof of work is submitted alongside a block by blockchain miners to prove that a certain amount of computational power has been spent to validate and create a block. Now, proof of work is really what lays the foundation for the security on blockchain networks like Bitcoin, although it's used on many other networks as well. By providing a certain amount of work or proving a certain amount of work has been done, the blockchain network continues to get more secure over time because more and more work has been done on that network. For someone to then go and try to change the blockchain network or do something malicious with it, they would have to provide that same amount of work and actually even more. So the more work that is added to the blockchain network, the harder it is to change. And that's what provides a lot of the properties of blockchain networks that we heard previously, like immutability. So before we go any further, let me just give you a high-level overview of the blockchain network as a whole and the role that miners have to play. Then we can kind of understand what a miner is and what it's actually doing when it's submitting a proof of work. So let's say that we have a few clients on the left-hand side of our screen. Now, these aren't miners. These are just people who are using the blockchain network. Maybe they want to be submitting transactions. Maybe they have a wallet on the blockchain network. Doesn't really matter. These are just people that are kind of on the network. So then at the top of our screen, I'll just draw a few blocks here, and this will kind of represent our existing blockchain network. And obviously, there'd be some more blocks before that. All right, so that's our blockchain. These are our clients. And then as we recall, we have this transaction pool. Now, really, this pool is going to be held individually by every miner. And actually, let me draw those out right now. So our miners will be kind of these purple blocks here. All of these are our miners. Now, all of these miners will have their own version of a transaction pool. But for now, let's just keep it simple. And let's imagine that there is a single transaction pool, and all of these miners are kind of reading from that pool. Again, this would really be held individually by the miner on their computer. And they would be just kind of plugged into the network and creating this pool as transactions came in. But to keep it simple, we'll just draw one. So let's say that our clients here are sending transactions to the pool, or they're sending it to the network. So they're all sending transactions. And once those transactions are sent, they get added into the pool, as we know, and they then wait to be picked up by miners and then added to the blockchain network. Now, what miners are doing is they're reading from this transaction pool, and they're gathering transactions and assembling them into blocks. So all of these miners at the exact same time are going to be grabbing transactions, usually based on the transaction fees that are associated with these, and they're all at the exact same time going to be trying to create blocks using these transactions. So this guy will be trying to make a block here. So will this guy, and let's just draw some transactions to kind of distinguish between the miners and the blocks. And they're all trying to create these blocks. Now, creating these blocks is very fast. All they have to do is look at these transactions. They have to validate that they are secure based on the previous block in the blockchain. So they have to make sure no double spending's going on and all of those different things we talked about in the previous video. And then they're going to assemble a block with the valid transactions. Now, once they've done this, they need to submit a proof of work alongside this block to be able to try to add it to the blockchain. Now, this proof of work essentially involves guessing a very specific number. We're going to talk about that in a second, but just imagine that all of these miners here, they're all racing to try to get this proof of work so that they can submit the block. Now, all of the blocks that you see here, they could be the same, but they also may be slightly different because all of these miners may have a slightly different version of the transaction pool, and they may be grabbing different transactions. So all of these blocks are being created by these miners kind of locally on their own machine. And right now, these are tentative blocks. They're not yet on the blockchain. So these miners are now racing to try to guess this number and try to find a proof of work for the block. So let's just label our miners here to make this clear. So let's say miner 1 actually finds a proof of work for this block. Once they do that, they then transmit this block to the network and they wait for it to get added. Now, for it to get added to the network, the other miners need to validate that the transactions on this block are secure and that the block itself has a valid proof of work. If that's the case, then this block gets added to the blockchain. So let's take this and move it here. So I know this is a little bit rough, but you know what I mean. So that gets added to the blockchain. And then what happens is all of these miners need to pretty much erase the blocks that they are working on, and they need to start trying to mine a different block. Because now they're going to see, okay, This new block has just been added to the network. That makes the blocks that they would have been working on likely invalid. In fact, it will make them invalid because those blocks need to contain the previous block hash. So then they go again, they grab whatever remaining transactions there are, they assemble them into a block, they continue trying to guess the proof of work and submit that to the network. So that's the basic flow of what's going on here. Now, the reason these miners are doing this is because if they successfully add a block to the network, they get a reward. So this guy would get a reward of 6.25 Bitcoin plus whatever the transaction fees are. Now, that's actually quite a large amount, so that's why there's a massive incentive to be a miner and try to submit valid blocks to the blockchain. All right, so now that we hopefully understand the basic idea of what's going on here with miners and people submitting transactions and kind of the flow of the network, let's look at what actually is involved in finding a proof of work. What is meant by proof of work? So let's clear the screen and have a look at that. So on our blocks, we have a bunch of information, right? We know that we have our block header. We have things like the version of the block. We have the previous block hash. We have all kinds of data. And then, of course, we have all of the transactions that are associated with this block. Now, as I said, what a miner is doing is it's sitting on the network and it's listening for any transactions. So again, we can have our miner here, and this miner has its own transaction pool, which is really just running in the RAM or the memory of this miner. It could be stored on storage as well, depending on how large the pool is, but typically it's sitting in some form of fast access memory. So it has this transaction pool, and anytime a new transaction is broadcasted to the network, it gets added into this miner's pool. Now, this miner is constantly trying to build blocks containing these transactions, find the proof of work, and submit them to the network. So once they build a block here and they add different transactions onto it, what they need to do first of all is they need to validate that all of the transactions that they're adding are indeed valid. Now, they do that by checking the signature, but they also need to ensure that there's no double spending going on. And in order to do that, they have to have access to the previous block in the blockchain. Because if the previous block had, say, this same transaction, then if they try to submit that alongside this block is going to be rejected by the network because that's a double spend and it's an invalid transaction. So I just want to give you kind of a basic idea of how that goes on. So anyways, they have to have access to the entire blockchain and all of the transactions that are coming in. Now, let's imagine at this point that they have actually created a valid block. So based on the previous blocks and based on the transactions here, everything is valid, and now what they need to do is find the proof of work. Well, what is the proof of work? The proof of work is simply a number that makes it so when this entire block is hashed, that the hash starts with a certain amount of zeros. So this is when we're going to talk about the nonce and the bits. Now recall that the bits on a block is simply the difficulty for this block. Now these bits, let's say, is equal to something like 20. If you see 20 bits, what that means is that the hash of this block must start with 20 zeros for it to be a valid block, for the proof of work to essentially be submitted. Now, the thing is, when you hash this block, you're going to get some kind of random value, and the odds that it's going to start with 20 zeros is practically impossible. It's just really, really unlikely that it's going to start with 20 zeros. So what you need to do is you need to add a special number to this block that makes it such that the hash of this block does start with 20 zeros. Now, that special number is the nonce. So essentially what's happening when someone is mining is they are determining a bunch of nonces, or they're guessing a bunch of nonces to add to this block such that the hash starts with 20 zeros, in this case, because that's the number of bits. Now, really, they're just trying to find a number that is prefixed with the number of bits. So if it's 10 bits, they need 10 zeros. If it's 30 bits, they need 30 zeros, etc. And that's what determines the difficulty of the network. And that's because every time you add a zero, it becomes more and more challenging to determine a nonce such that the hash of this block starts with that many zeros. So hopefully that makes sense, but that's really all that's going on when you are mining. You are guessing a ton of different numbers, thousands, millions per second, pretty much, depending on the speed of your computer, and adding that number to the block, hashing the entire block, and hoping that it starts with 20 zeros. Now, if it does start with 20 zeros, then you submit that block because you now have a valid proof of work, and you have found a number that makes the hash of the block plus that number start with 20 zeros. And when I say the hash of the block, this number is included in that block, right? So you're hashing all of the data I talked about in the previous videos, plus the nonce, and that gives you a number that starts with the number of bits. When that happens, you have a valid proof of work, you submit the block to the blockchain, and then assuming that all of your transactions were indeed valid and that the hash of this block is valid as well, you will receive your reward, and this will get added onto the Bitcoin blockchain network. All right, so now that we've looked at that, let's look at an example where we have multiple miners and see how these miners work together. Now, to make this simple, we'll just draw 3 miners. So 1, 2, 3, and this can be miner 1, miner 2, and miner 3. Now, all of these miners are actually storing their own version of the blockchain. So remember, we have a decentralized distributed ledger, which means that all of these miners are storing their own version of the blockchain. Now, what we also have on these miners, other than the actual blockchain, is we have their transaction pools. So I'm just going to represent these with circles inside of the miners. These are the TX pools. All right, now let's draw, a little stick figure guy. Let me give myself a bit more room here. And this guy wants to send a transaction. So what he would do is he would take a transaction and he would broadcast this out to the network. Now, since these nodes, which are the miners, are sitting on the network, they're going to be listening for transactions and they're going to receive this. So the transaction is going to go into all of their transaction pools and they'll kind of write it in here. And in fact, we can just write TX, TX, TX. All right, so now our miners have this transaction. Now, they would have already been doing this, but we're just imagining we're starting right from the beginning here. What these miners now do, because they have a few transactions in their pool, is they start trying to build a block with these transactions. So all of them are going to be creating kind of tentative blocks that have these transactions, and then trying to find the nonce for these blocks, which they can submit as a proof of work. So now that we understand the transaction gets submitted here, let me just delete this guy so we have a bit more room. All right, so they're all building this block. Building the block is relatively simple. It's pretty fast for them to do that. But before they can build this block, they need to validate that all of the transactions they're adding are indeed valid. And the only way they can do that is by having a history of the blockchain. Because if this transaction was already on, say, this block that they're storing, then they know that they can't add it to this block because it's going to be rejected by the network when they try to submit it. So it's just important to understand that they have to have an up-to-date version of the blockchain to be able to assemble and find a proof of work for a block. If they don't have an up-to-date version of the blockchain, then they're not able to ever submit a valid block because they would have double spends and invalid transactions and all of that kind of stuff. Okay, so let's imagine now that miner 1 successfully finds the nonce that makes this start with a specific number of zeros, whatever the bits is. What he's going to do now is he's going to broadcast this block out to the network. Now, since these miners here are listening to the network, just like they get transactions, they're going to get this block. So this block is going to go to both of these miners. Now, these miners, they're going to look at this block and they're going to see if this block is valid or not. Now, if this block is valid, they're immediately going to delete the block that they've been working on, and they're going to add it to their blockchain. So let's imagine this new block is just like a yellow one. They would tack it on to the end. So now that it's here, they're able to work on a new block with new transactions and continue the process of mining. Now, that's scenario 1. The block is valid, they add it to their copy of the blockchain, and then they continue trying to mine new transactions or new blocks. Now, in scenario 2, this block is not valid. Now, if the block is not valid, what they're going to do is they're going to reject adding this to their copy of the blockchain. So let me just cross it out here. Now, if that's the case, they would have not deleted the block that they would have been working on, and they're going to continue trying to guess the nonce and find the proof of work so they can then submit that block. Because they don't want to delete this block if the block being submitted to them is invalid, because this block could still potentially be valid. In fact, based on their version of the blockchain, it is valid. So they're going to continue trying to guess the nonce for that block. And only in the scenario where a new valid block is submitted to them do they delete this block. Otherwise, they're not going to delete it, because why would they do that? They're going to keep working on the block, hoping that they get it first. All right, so hopefully that makes a bit of sense, but this is really what's going on here, right? We have a bunch of different miners. They all store their different versions of the blockchain. Now, really, these blockchain versions should be in sync, but they are going to be potentially slightly different based on a bunch of different factors. Anyways, all these miners have a version of the blockchain. They're constantly looking at their transaction pool. They're removing transactions from that pool that are already on the blockchain, whether they added them or someone else added them, and they're trying to create blocks with transactions and then find the nonce for those blocks, which is really the proof of work, and submit that to the blockchain. As soon as someone else submits a valid block, whatever they were working on kind of goes out the window, and they restart the process and they try to guess for a new block. So there's a competition going on where they're racing to try to guess the block, and really the race is based on probability. Whoever has more compute power, more ability to guess numbers, is going to have a better chance of guessing the nonce and hence getting the reward. So that is the high-level overview of how these different miners communicate with each other. Now, though, let's have a look at some edge cases and see what can happen when multiple miners submit blocks at the exact same time. So in the previous example that we looked at, we just had 3 miners. It was fairly simplistic, and the probability mathematically that these miners would guess the nonce for a block at the exact same time was extremely low. Now, of course, on the actual Bitcoin blockchain network, we have hundreds of thousands, if not millions of miners. So the probability that 2 miners could be submitting a valid block at the same time is actually fairly likely. And that happens approximately every week on the Bitcoin network. So you can determine if you think that's likely or not, but it happens enough that we need to consider what happens when that is the case. This is kind of an edge case, but we need to know what happens then. So let's just write out a few miners here, and we'll go with 3 again, but imagine we had many, many more than this. And let's say that in the middle of the screen here, this is kind of the current agreed upon version of the blockchain. Now remember, this is really being stored by all of these miners individually. We'll imagine that all of these miners currently at this point in time agree that this blockchain is the current valid version. They agree, there's no debate, all of the blocks here are finalized, and yeah, they're in consensus about that. So now our miners are working, they're guessing, they're validating transactions, and let's say that both of these miners find a valid block and they determine the nonce and the proof of work. Now at the exact same moment in time, they submit these blocks. What actually happens in this scenario? Well, let me give myself a bit more room. So if this is the case, what happens, and actually, let me just draw this in green to make it a bit more clear, is we create what's known as a fork chain. Now, that means that we're going to have 2 versions of the blockchain that look something like this. Because both of these blocks are submitted at the exact same time, both of these blocks were valid, we have no other option really than to add them both onto the chain. Now, the reason why you actually see this fork chain here is because what's going to happen is some miners on the network are going to accept this green block as the current valid block, and some are going to accept this orange block. And that's probably going to have to do with latency and when the blocks are actually received on different miners. But what will happen is a bunch of miners will have the green version, and a bunch of miners will have the orange version. So we write this fork here just to demonstrate the fact that different miners are storing different but both valid versions of the blockchain. Now, on both of these blocks, we could have duplicated transactions, all kinds of weird stuff could be going on. So now, how do we resolve this problem? How do we get back to having a flat blockchain and determine which one is going to be valid? Well, the way that we resolve this issue is by waiting for the next block to be submitted. So let's say, right, that this blockchain here, well, it's going to be storing, actually, this one would be storing the green version, this one would be storing the yellow version, and maybe this one's storing the green version of the blockchain, okay? Now, if the next block is submitted that's valid from this node right here, from this miner, then what happens is this chain becomes 1 block longer than the orange chain. Now, nodes are told to always accept the longest chain. Now, the longest chain does not only have to do with the number of blocks. I'm going to give you a more precise definition in a second. But since the next valid block was submitted by a miner who was using this as the previous block, this now becomes the longest block, or the longest chain, on the blockchain. And now all of these other miners receive this new white block, and this guy here who is storing the yellow version of the blockchain has to delete his yellow version and go back to reading the current valid version of the blockchain. Because if he were to stay on this version of the blockchain, now it's going to be out of date versus this, and he's never going to be submitting a valid block because he's going to be using this as the previous block when that's not the case. Now, this is the previous block. Hopefully this is making a little bit of sense, but essentially the resolution occurs when the next valid block is mined. And since it was mined by a node that accepted this as the correct version of the blockchain, now this whole chain right here is the valid chain, okay? Because it's the longest chain on the network. And if someone else tries to add to this chain, it's going to be considered invalid because the previous block hash of whatever block they add is going to be wrong versus the current longest chain. So hopefully that's making a little bit of sense. Now, though, let me define what I mean by longest chain because it's not quite as simple as the number of blocks. So I've just cleaned up the screen here, but continuing, the longest chain, which is what all of our nodes are supposed to be using as their current version of the blockchain, is really the chain that has the highest cumulative difficulty that is valid. Now, those are two very important points. First of all, the chain must be valid. What that means is there must be no double spends. There must be all valid blocks, all valid transactions. If you have any invalidity to the chain, it doesn't matter how long it is. It's not the longest chain because it's invalid. It's not a proper chain. So first aspect, the chain must be valid to be considered the longest chain. Second, it has to have the highest cumulative difficulty. Now, the highest cumulative difficulty refers to the amount of proof of work. So really what this would mean is summing all of the bits on all of the blocks that are in that chain. So if this chain, for example, has less difficulty than this chain, then this one here would be accepted as the longest chain because it has a higher cumulative difficulty. And the blockchain wants to encourage more proof of work because the more work that's been done, the harder it is to modify or change the blockchain because that work would have to be redone, which we're going to get to in a minute. But you need to understand that what you really do is you take the number of bits. So let's say this is 1 bit, 2 bit, 3 bit, 4 bit, 5 bit. You would sum all of the bits on all of the blocks in this chain, and that would determine what the cumulative difficulty of that chain is. Whereas let's say this had 100 bits. I know that would be unrealistic, but even if it did, you would take this as the longest valid chain because the highest cumulative difficulty comes from this chain, not from this top chain. So usually it does correlate with the number of blocks that are in the chain because the difficulty of blocks should be similar. And we'll talk about how the difficulty increases in a minute, but just keep that in mind. The definition formally is the highest cumulative difficulty valid chain. That's what you're selecting as the longest chain. So hopefully that makes a bit of sense. Just to summarize one more time here, if there's a situation where nodes submit blocks at the exact same time and different miners have different versions of the blockchain, and this does happen fairly frequently, the way this is resolved is by the next valid block being submitted. Now, usually the next valid block is not going to be submitted at the same time as another block. So you're not going to have a scenario where you have two blocks being submitted at the exact same time on different fork chains. Now, if that were to happen, then the resolution again is the next valid block to be added and whatever that chain gets added to. So whatever chain has the highest cumulative difficulty and is valid is what should be continued throughout the blockchain. So this chain would kind of be erased or deleted, and anyone that was continuing to work on that chain would never be able to come up with a valid block because it would not be added by the rest of the miners. It wouldn't be accepted because they're working on an old version or a fork chain that was not continued, which sometimes is referred to as an orphaned chain. So just to add one more small point here, some of you may have seen when sending transactions on blockchain networks that you have something called confirmations. Now, the number of confirmations that a transaction has is actually the number of blocks that have been added in the blockchain since that transaction. So if you were on, say, block 2 or your transaction was on block 2, and now the blockchain's on block 5, that transaction would have 3 confirmations. And the more confirmations a transaction has, the more confident you can be that that transaction is on the blockchain and isn't going to be reverted back to, because it could have been added onto, say, a fork chain, which would then have been removed later on. Whereas if you have 3, 4, 5 confirmations, the probability that this is on a fork chain is extremely low due to the fact that it is difficult to continually create the fork chain, like we talked about before. So just understand the number of confirmations is the number of blocks that have been added since the block that contains your transaction. Now what I want to talk about is difficulty of the network and hashing time. So as I was saying, the number of bits that you have is the difficulty for a block. Now, this difficulty, the block difficulty, is adjusted every 2 weeks on the Bitcoin blockchain network based on the volume of the network. Now, what I mean by that is that Bitcoin wants to have an average block time of 10 minutes. So they want one new block to be created every 10 minutes. Now, this is going to vary how long it takes to create a new block based on the number of miners that are currently on the network. So if you have more miners, you have more hashing power, you have more compute power, and your time is probably going to get lower. Now, if that's the case, you need to increase the number of bits so that the time goes back to be approximately 10 minutes. Now, there's mathematical formulas that can do this, and every 2 weeks, the number of bits is adjusted based on the average block time to try to make that average block time go back to be 10 minutes. So it uses the hashing power of the entire network, which is essentially how many computers are on the network and how fast those computers are, all summed up, and then it tries to make it so that that's going to take approximately 10 minutes to mine a new block. So that's how the difficulty is adjusted, and the difficulty of the Bitcoin network can increase or decrease over time depending on the volume of the network. All right, so I've just cleared the screen, and now that we've gone through kind of the fundamentals about mining, and you should understand how that works, I want to talk to you about mining strategy. Now, mining strategy refers to how a miner is going to most efficiently attempt to find a valid block and to submit that to the network. Now, you have to imagine when we're talking about a network like Bitcoin, we have, tens of thousands, hundreds of thousands, maybe millions of miners. I don't know how many miners we actually have, but it is a significant amount. Now, what that means is that if you're a single miner and you're just maybe one computer, you have a single graphics card, whatever, you're a very low output miner, you don't have a whole farm or something, your probability of mining a block is extremely low. And that is just because there is so many different miners on the Bitcoin network that the chance that you're going to be the first one to guess a valid block every 10 minutes is just extremely, extremely low. So what do you do to compensate for this or to fix this problem? Well, what you do is you join a pool. Now, pool mining is a large debate because there is some disadvantages with pool mining, which I'll get to in a second. But pool mining essentially involves pooling the resources of multiple people and increasing the chance of mining a block while distributing the rewards based on the amount of work that was done. So in pool mining, you essentially have a large pool of miners. So rather than all these miners sitting individually trying to guess a block, they pool all of their resources together and attempt to mine blocks. Now, pools can be massive. They can contain like 10, 20, 30% of the total hashing power of the entire network. And by the way, hashing power is usually the metric we use to determine how quickly something can hash. So if you hear gigahash or terahash or megahash, that's just a unit of how quickly you can be guessing nonces and determining if the hash of a block is valid. That's really what it means when I say hashing power. So what they do is they pool all of these miners together, and then this pool collectively mines blocks. And then what happens is these miners are paid out based on how much hashing power they contributed to the pool. So if the pool had 100 megahash total of power, and each miner was contributing, say, 10 megahash, then that would mean that each miner would get 10% of the rewards that was generated by the pool, whether or not they were the one to mine the block. So it doesn't matter if each individual miner actually ends up mining a block, they're just getting rewarded based on how much hashing power they're contributing. So if you're only contributing 5, then you're going to get 5% of the rewards. If you're contributing 50, you get 50% of the rewards of the pool. And that's, 50%, of the 100 mega hash. Anyways, that is how pool mining works. Now, the issue with pool mining is that this reduces the decentralization of the network, because as you pool resources together, you now have some entity, which is the pool essentially, because the pool is typically some type of central server that's facilitating all of this reward payout that's controlling a large majority of the network. So on networks like Bitcoin or Ethereum, you have very large mining pools which control large percentages of the entire network. So if that pool were to go down, you would lose a massive volume on the actual network of miners. And if that pool were to be hacked or something, then again, you'd be having a huge security risk. So pool mining is good if you're the miners, but it's bad for the network as a whole due to the decentralization. Now, there's all kinds of arguments and debates. But really, you just have to understand that when you mine in a pool, you get a share of the rewards based on how much you contribute. And you reduce decentralization because everyone is pooling resources. And if a pool were to control over 51% of the network, it would have complete control. It could do whatever it wanted to do. So that is the first part to talk about in terms of mining strategy, joining a pool. But now I want to get down more to the mining client level and discuss what actually happens a bit on a lower level as a miner is, well, mining and being connected to the network. So just to understand here, there's a bunch of different pieces of software, which we call clients, which pretty well anyone can run on their computer. If you want to be a Bitcoin miner, you don't have to write code, you don't have to be technical, you just have to follow a few instructions and download one of the many Bitcoin miner clients that exist. So you would download this client, again, which is a piece of software, and then that runs on your computer. Now, what these clients will do, at least if they're optimized when it comes to mining different coins, is they will be creating empty blocks. Now, I know this is going to seem a little bit weird, but I want to talk about why that's happening. So let's say that we have our miner, okay? Our miner has their own transaction pool, which is really just running in some form of memory, and then they have an entire history of the blockchain. Now, they may not be storing that entire history, but they have access to it, or they would have ran through it at some point in time. So they'd be kind of skimming through the blockchain history. Again, I won't get into exactly how that works, but they're storing, the most recent blocks, right? So they have some version of the blockchain. Now, this miner is going to be listening to transactions coming in, and it's also going to be listening to new blocks that are submitted. So transactions are going to be submitted and new blocks are coming in as well, and it's listening for all of that. Now, at the same time, it's trying to create blocks and submit that to the network. Now, in this scenario where a new block is transmitted or submitted to this miner here, what happens is this miner needs to take a second to review this block and all of the transactions on it and see if any of the transactions that are on it are included in its transaction pool. Because if any transactions are on this block but also in its transaction pool, it needs to remove them from the transaction pool so that it doesn't accidentally add them to another block and then submit an invalid block, because it only wants to be working on blocks that are actually going to be able to be submitted to the network that are valid, assuming it's not a malicious entity. So that's what's happening. Now, this takes a certain amount of time. This could take a second, it could take a few milliseconds, whatever the time period is. So in the time when it's reviewing this new block, it's not able to know which transactions it should add to a block, right? Because it's reviewing this one and it's kind of cross-referencing the transactions between its pool and the new block that just got submitted. And yeah, in this time, it's really not able to create a new valid block because it doesn't know what transactions are happening. So what it does instead is it creates an empty block. Now, the reason it creates an empty block is because it knows what the previous block hash is going to be. It just doesn't know what transactions to add. But it can submit a block that's valid to the network so long as it has the correct proof of work, even if that block contains no transactions. So in the meantime, it creates an empty block, and it starts trying to guess the nonce for the empty block. Now, if it guesses that nonce, this is a valid block, and it can submit this to the blockchain as a block that contains no transactions. I know this seems a bit weird, but the blockchain doesn't care if the block has 1 transaction or 5 transactions or 0 transactions. All it cares about is that every block that's added to the chain adds more work. It adds further proof of work to the blockchain network. So even if this block is empty, it's still adding to the security of the network because it's increasing the proof of work and it's extending the length of the chain. The longest chain gets longer, the difficulty increases, the cumulative difficulty, and it's fine to add that block on. So in the time period of usually 1 to 2 seconds, while it's looking through this new block that's coming in and cross-referencing transactions with its transaction pool, it's still going to be mining on an empty block. Now, as soon as it finishes doing this, so the 1 to 2 second period is done, and by the way, it could be much less than this or longer, just depends on a bunch of different factors. I'm just estimating here that it would be, around 1 second it would take to do that. So after that finishes, that 1 to 2 second time period, it then will find the transactions and add those onto the block. Now, the reason it would do this again is because it wants to be trying to mine and submit a block at any point in time, and its probability of finding the nonce for a block that contains transactions is the exact same as finding the probability for a completely empty block. So if it changes from trying to find an empty block to trying to find a block or trying to find the knots, for a block that contains transactions, it doesn't reduce its progress. It doesn't make it any slower or any faster. It's the exact same probability that it's going to guess the knots for this block as it is for this block. So in the time where it's waiting to check the different transactions, it will be trying to mine an empty block, and to mine the block is just to find the proof of work. And if it finds that, it will submit that to the network. So if you look at a lot of proof of work networks, you'll see that empty blocks are added all of the time because this is happening. And again, those networks don't care if there's an empty block, because the more blocks and the more difficulty that's added to the network, the harder it is to hack and to change that network. All right, so that is the basis there of kind of mining strategy. Now, the next thing to quickly talk about is the environmental impact of proof of work. Now, with proof of work, there is a ton of repetitive and redundant work being done. So if you look at these miners, first of all, we understand that what they are doing is they are trying to guess a bunch of numbers. Now, the faster computer you have, the more compute power you have. It can vary based on the type of compute power, but let's just generalize and say the more compute power you have, the faster you can guess numbers. It also means the more electricity and power you're going to be using up typically, right? So all of these miners are working on very similar blocks at the same time. And only one of these blocks, maybe two or three if they're submitted at the same time, but let's generalize and say only one of these blocks every single time is going to be valid and submitted to the network. And then these miners are going to essentially delete what they were working on and go on to working on something else. So these miners are continually doing a ton of work that really doesn't matter, that doesn't do anything for the network, in the hope that they are going to be the one that submits a valid block. So if this guy submits his valid block, all of these become invalid, and all of the work that these miners just did is completely useless for the network, and it really was wasted computational resources. And continuing with that, it would waste a ton of electricity, because all of the power that went into doing that was just wasted. It was really for no good. So this is a huge argument against proof of work algorithms, and why a lot of new cryptocurrencies and even existing ones like Ethereum are going to be going to the proof of stake algorithm, which we're going to talk about in this next video. So proof of work is not a bad or evil algorithm, but it definitely is not the most environmentally friendly. And there's a lot of people that are very upset at networks like Bitcoin and Ethereum for utilizing this type of algorithm because of the amount of energy waste that it has. All right, so that is almost it here. The very last thing I want to talk about is how someone would try to hack a proof of work network. So as we saw before, what can happen when we have a blockchain network is we can have fork chains, right? Where we can have a chain here and a chain here, and actually, let's just do them in different colors. Okay, so when we have a fork chain, as you recall, the chain that's going to be continued and live on is the one that the next block is added to. So the way that people would try to hack a proof of chain or a proof of work network, is they would try to continue an invalid chain as long as they possibly could. Now, the thing with this is that for them to be able to do that, they would need to control 51% of the network. Now, the reason they would need to control 51% of the network is they would essentially have to be outworking and outproving everybody else trying to continue a fraudulent or malicious chain. If they have 51% of the network, then what they can do is they can continue this chain indefinitely because they have enough validators, enough miners to continually add new blocks to the chain and to accept these fraudulent blocks as the next valid block in the chain. So hopefully that makes a little bit of sense, but what would happen when you're trying to hack the network if you were doing a 51% attack is forks would occur, right? And you would just continue an invalid or fraudulent chain as far as you possibly could. But to be able to do that, you're essentially racing against the rest of the network. So you have to have more power than them. Otherwise, they will be able to invalidate your chain and realize that this is a fraudulent chain, should not be continued, and then they'll continue the other chain with the valid block that would have been submitted. So hopefully that makes a little bit of sense, but that's kind of what's going on here when we're talking about 51% attacks and trying to hack the blockchain network. You have to be able to control a majority of the network with something like proof of work to be able to do something like that. Otherwise, your chain is not accepted because it's not the longest chain. All right, so with that said, I'm going to wrap up the video here. I know this was long and there was a lot of information, but this is a very important concept and I wanted to go into as much depth as possible so you really understood the security basis of the blockchain network and what's going on when we talk about mining and proof of work. With that said, I hope you enjoyed, and I look forward to seeing you in another Blockchain Expert video.